going to go ahead and review the law of exponents back from Algebra 1. These ideas will be very, very important for our future topics. So let's look at the first statement that they give us. Here, notice that you have 2 to the third power being multiplied by 2 to the second power. And what they want you to do is figure out if this statement is equal to 2 to the 6th power. So one way we can go about this is really just expanding the multiplication here on the left-hand side. Let's go ahead and do that over here. So 2 to the third is the same thing as saying 2 times 2 times 2, multiplied by itself 3 times. And then we have 2 squared. So we'll go ahead and add in another 2 multiplications of 2's right here. So here, once again, we have 2 to the third from this group, and then 2 to the second power from that group. But notice, though, when you count up all the 2's here, we have 1, 2, 3, 4, 5. We have only 5 2's that are being multiplied by each other. So in reality, this is actually equal to 2 to the 5th power, because we only have 5 2's being multiplied. So in fact, this statement will be false. In order to correct this statement on the side here, we'll go ahead and say that 2 to the third multiplied by 2 to the second is actually equal to 2 to the 5th. Okay. Let's go ahead and look at the second one right here. This is saying 2 to the 5th multiplied by 2 to the 4th is equal to 2 to the 9th. So here, let's go ahead and expand these together. So here we'll have 5 2's being multiplied by each other. And then we'll have 4 2's being multiplied by each other. Once again, this is 2 to the 5th. And this is 2 to the 4th. If you count up all the 2's that are being multiplied, we have a total of 9 2's. So in reality, this would equal 2 to the 9th. If you look at the statement here, this statement is actually true. Okay. So what I want you to see here is that there is a pattern that occurs. Notice here that the exponents are being added together, ultimately. So that's one thing I want you to think about, and we'll generalize that in just a moment. Let's go on to the third one. Here now we have a division going on. We have 4 to the 5th power on the top, divided by 4 to the second power on the bottom. Once again, let's go ahead and expand that and see what we get. So we have 5 4's on the top being multiplied by each other. And then we have 4 2's being multiplied by each other on the bottom. One thing I want you to see here is we want to see if any of these 4's will cancel out when we have division. Notice here we have 4 divided by 4. That'll give us 1. So that will go away. We have another set that'll also cancel out. Ultimately, we're left with 3 4's that are being multiplied by each other. So that'll be 4 to the third power. So indeed, this statement right here is true. So one thing I want you to look at here is think about what happened to the exponents. Did they add together? Did they subtract by each other? So just think about that. Let's go ahead and look at the next one. We'll go ahead and do the same process. So here we have 5 to the 4th divided by 5 to the 6th. We'll expand that. 5 times 5 times 5. And then we have 6 of them on the bottom. Here we think about the cancellation process once again. These would cancel, these would cancel, these would cancel, these would cancel. Notice though that we don't have any 5's on the top. In this situation, this is the most important part. Please don't forget there is actually a 1 on the top when this occurs. Because we still have 5 divided by 5, that'll give us 1. So we have 1 on the top. But on the bottom here, we have 2 5s, so we have 5 to the second power. And indeed, if you look back at the statement, this will create a true statement. And we can keep on going just a little further. This will also equal 1 over 5 times 5, which is 25. So if you can simplify a little more, go ahead and do so. But most important thing here is, if you look back at this first one, here we subtracted the exponents when there's a division to get our new exponent right here. So 5 minus 2 is 3. And then here, 4 minus 6, be real careful with that one. That'll give us 5 to the negative 2. So I want you to be thinking about these right here. But 5 to the negative 2 is also equivalent to 1 over 5 to the 2. Okay. Let's go on to the next one. 2 to the 0 power is equal to 0. Is this statement true or false? So here, one way we can go about solving this out is setting up a little table. And in this table, let's just say I start out with 2 to the first power. 2 to the first power is just 2. 2 to the second power is 2 times 2, which is 4. And then 2 to the third power will give us 8. One thing I want you to notice, though, as we go from the right to the left, to go from 8 to 4, we're dividing by 2. To go from 4 to 2, we're also dividing by 2. So one way we can go ahead and approach this statement is, if we want 2 to the 0 power, we're still going to go ahead and descend in terms of our exponents. So same idea. To go from 2 to this number right here, we'll also divide by 2. And 2 divided by 2 is just equal to 1. So here, 2 to the 0 power would equal 1. So this statement would be false. And we'll correct it over here by saying 2 to the 0 is actually equal to 1. All right, let's go into the next one. Here, be real careful with this notation. This is 4 to the third being raised to another exponent of 4. We're going to see if this equals 4 to the 7th. So one thing I want you to think about here is that 4 to the third is being raised to the 4th power. Another way we can rewrite this in terms of our groupings is say that we have 4 sets of 4 to the third being multiplied by each other. And notice here, each of these are being raised to the 3rd power. That means we have 3 4s being multiplied here, another 3 here, another 3 here, another 3 here. So in reality, we have 12 4s being multiplied here. So this would equal 4 to the 12th power. So this statement right here would be false. 4 to the 3rd raised to another exponent of the 4th is actually equal to 4 to the 12th power. And one thing I want you to notice here in this statement is, think about what's happening here. How do we get to 12? Well, here we'll multiply 3 and the 4. All right, so we're almost there. Let's go on to the next one. Here we have 3 to the negative 1 is equal to 1 over 3 to the 1. We want to know if this is true or false. Here, once again, we can think about setting up this table that we set up earlier for this situation. Let's just say I go ahead and do that. And let's just say I started with 3 to the first power. That is 3. 3 to the second is 9. 3 to the third, if you plug that in a calculator, will give us 27. And once again, if we want to descend in terms of our exponents, notice here that our values, as we go from 27 to 9, we will be dividing by 3. Same as well over here. 9 to 3 will divide by 3. So in order to get 3 to the 0 power, we'll also divide by 3. 3 divided by 3 will give us 1. And then now, let's descend one more time to get 3 to the negative 1. That must mean that we're dividing 1 by 3 again. 1 divided by 3 is just 1 over 3. So, if you look back at the statement, 1 over 3 to the first is the same as 1 over 3. We don't really have to write that exponent in, so this statement would be true. And one thing I want you to think about here is, think about how a negative exponent affects the value of this. Notice that when we have a negative exponent, we ended up with a fraction. So just think about that. Okay. All right, let's go on to the next one. Here we have 3 to the 5th. 3 over 5, 3/5, raised to the 4th power. We want to see if this is true. So here we can use that same analysis we said earlier with this. Here we have 3 to the 5th being multiplied by itself 4 times. Notice on the top we have 4 3s. That is the same thing as saying 3 to the 4th. And on the bottom we have 4 5s. That is the same thing as saying 5 to the 4th power. So indeed, this statement would be true. And I want you to think here about how the exponent is sort of distributing itself within the fraction. That'll be another important property we'll come across. All right, we're almost there. Next one, we'll have 7 to the 2 raised to the 3rd power is equal to 7 to the 6. True or false? And very similar analysis. Here we'll have 3 sets of 7 squared being multiplied by each other. And once again, here we have 2 7s, 2 7s, 2 7s. That'll total up with 6 7s. So this will be equal to 7 to the 6th power. So this statement right here is true. All right, and we're almost there. Last one on this end. Here we have 6 times 4, all being raised to the 3rd power. They want to know if this is true or false. Once again, we can expand it real similar to the previous one we mentioned before. Here we have 3 iterations of 6 times 4. So 1, 2, 3. If we regroup these, we'll have 6 times 6 times 6 times 4 times 4 times 4. And once again, we have 3 6s. That's just the same thing as saying 6 to the 3rd power being multiplied by 4 to the, we have 3 4s being multiplied by each other, so 4 to the 3rd power. So indeed, this statement is true. Right. So I want you to be thinking about these little rules that we've been coming across here. In general, we can generalize this. So please make sure you write this in. Anything raised to the 0 power. So when you write that. Anything to the power of 1. Anything to the power of 0. Anything to the power of 0 will always equal 1. So this would be very important. Let's go ahead and generalize the next rule. Here we have the same base, a, with different exponents being multiplied by each other. So here, if you look back at the first set of problems we looked at, this will be equal to a to the m plus n. So here we'll go ahead and add the exponents. All right, next one. Here there's a division. If you look back at the division, we had a subtraction in terms of the exponents. So this would actually be equal to a to the m minus n. So it'd be the top exponent minus the bottom exponent. All right. And then here, if you look at this next one, if you tie it into this example right here, if you have a fraction being raised to an exponent, we can kind of think of distributing the exponent into each number in the fraction. So this is equal to a to the m over b to the m. Okay. All right. And then over here, this property, if you look back at 4 to the third raised to the fourth, up here we notice that the exponents will be multiplied by each other. Okay. So that's a very important distinction right there. If you look at the next one right here, we can kind of think about this last one right here. There's sort of a distribution of the exponent in each of the numbers inside. So here this is equal to a to the m multiplied by b to the m. Okay. And final ones. This is the more tricky one. A to the negative m. Whenever there's a negative exponent, that'll introduce a fraction. That'll move the base to the bottom. Once we move this to the bottom of the fraction, the exponent will now become positive. And here we'll just have a 1 in this situation. So here all we're doing is we're moving whatever's inside to the denominator and raising it to the opposite sign of this exponent. Okay. All right, and the last one I want you to write in here is 1 over a to the negative n, a very similar situation to this one. But here now, this is in the denominator. So what will occur here is the a will move over to the numerator. And it'll jump up here, and then that'll make the exponent positive. So a to the m would be the answer here. Okay. So I want you to be thinking about these ideas. We will be using these exponent rules throughout the course. On the back side, don't worry about the quick notes. Most important thing is making sure that you're referring back to these rules right here. So what I'm going to go ahead and do is write in the answers to these questions right here. What I want you to go ahead and do is make sure that you complete this before our next class. But I'll go ahead and write the solutions down here so that you can check them yourself. As always, please let me know if you have any questions. I'm always happy to help.